Alright, hello, welcome back, and today we're going to be going into Lesson 2, Introduction to the Epsilon Delta Definition of a Limit. Remember in the last video we discussed what it generally means to take limits. However, we still only have an unproven concept that could potentially be based on unsound reasoning. So, imagine you're a mathematician at the time of the creation of the thought of the limit. You might be explaining to someone, so the limit as x approaches 2, or f of x gets closer to minus 3 as x approaches 2. You might be saying that. And a skeptic might respond by saying, are you sure? How can you prove this? Right? And right now, as it stands, the best thing you could say is, it seems to be that, right? If I take values very close, it seems to go very close, but we haven't proven that it does actually go infinitely close. And math is known for being a very rigorous system, where even propositions like 1 plus 1 equals 2, things that we take to be so trivial, must be proven. So let's relook at limits to create a complete definition. So let's take the limit as x approaches x naught of f of x equals to L. Say this is the graph that we're looking at. Here we have our L, and here we have our x naught. So recall that a limit is taking a neighborhood around x naught and tightening it until we see what y value is approached. So what y value will be approached? Well, that's known as our L, our limit. We tighten this purple region until we get an L. So let's create a variable epsilon such that we create a neighborhood, which is an area, a region. In this case, if you remember set notation, the limit minus epsilon, comma limit plus epsilon. Or in other words, this green region I've outlined here. So we define epsilon to be a variable such that we create that neighborhood, and we say the corresponding neighborhood around x naught. So the same idea here, but over here is a delta neighborhood, or delta. So we say our neighborhood is x naught minus delta. Notice we don't just say, like here, x naught minus delta, comma x naught plus delta, because we don't consider the value of x naught. If you remember from the previous video, we don't consider the exact value, we only consider values around it. So in order to include that, we have to go up to x naught and use an open parentheses back here. That way we indicate x naught is not part of the delta neighborhood. X naught is being excluded. But why do we do this? So I'm going to use the following analogy to explain how we're going to test a limit. In this case, we're going to talk about the example, the limit as x approaches 2 of x squared equals 4. Now let's play a game, per se. You are going to have to give me an epsilon, and I have to find a delta, such that any x that belongs to the interval, the delta neighborhood, so any x where x naught minus delta is less than x naught plus delta. This is just the meaning of this, but remember, x is not x naught. Keep that in mind. Has an f of x in the epsilon neighborhood we defined. So f of x where the limit minus epsilon is less than f of x minus the limit plus epsilon. Remember that, we'll reference that later in the video. So you say, how about we let epsilon be equal to 1? I have to find a delta such that all values is inside my delta neighborhood has a y value inside your epsilon neighborhood. So let epsilon equal 1. Well, here's our epsilon neighborhood. Can I find a delta neighborhood such that all values of x have y values inside here? Okay, let me choose delta equals 0.2. We have 1.8, and notice actually this graph isn't perfect, but actually if you take any value of x between 1.8 and 2.2 except 2, then we will have a y value corresponding to a number inside this epsilon neighborhood that you defined as epsilon equals 1. And in this case, our limit is equal to 4. Our limit is equal to 4. So how about epsilon is 0.5, you say? I'll say, okay, I'll choose delta equals 0.12. And I've calculated this, and I'm not going to show it to you, but in this case, it does actually work. Our limit is equal to 4, our delta is equal to 0.12, epsilon 0.15, and there is a neighborhood, specifically the delta I gave, inside with y values all inside, here and here. So all of this is inside of our epsilon neighborhood. Therefore, for the 2 epsilon values you've given me, I can find a delta. So let's say this game went on forever, for any epsilon you say, right? The limit, so we say that the limit exists and is equal to L, if and only if we continue this game forever, I can always find a delta. So for all positive epsilon, there exists some positive value for delta, such that if x belongs to the delta neighborhood, this is just saying x belongs to the delta neighborhood, right here, then f of x belongs to the epsilon neighborhood. This is what it is. That f of x is between the interval limit minus epsilon, limit plus epsilon. And that's the real definition of a limit. We can go as close to L as we want, including infinitely close, yet we can still find a neighborhood around x so that our corresponding f of x is in the epsilon neighborhood. So let's redefine our definition. Firstly, though, we'll go over a few things to convert set notation into inequality. Fx belongs to this interval right here, so the limit minus here, we can just, if and only if, the limit minus epsilon is less than, remember we have open parentheses, f of x, which is less than, again open parentheses, L plus epsilon, we'll subtract L from all sides. We'll get minus epsilon is less than f of x minus L is less than epsilon. And by the conjunctive inequality of the absolute value, if you don't recall, the conjunctive inequality says that if the absolute value of x is greater than or equal to k, or in this case the absolute value of x is less than k, the if and only if minus k is less than x is less than k. So x belonging to the delta neighborhood right here implies this inequality where x is not equal to x naught, very important. If and only if negative delta is less than x minus x naught less than delta, we'll subtract x naught from all sides. Remember, taking into account x is not equal to x naught, it's excluded from the interval. If and only if the absolute value of x minus x naught is less than delta, and remember x is not equal to x naught, if and only if this is true, we add a 0 less than, because the only way that this could possibly be equal to 0 is if x is equal to x naught, which is not true, so it's not equal to 0, so we have to write greater than, and it's an absolute value, so it's always greater than or equal to 0. Let's rewrite this definition into more math terms. So I'm just copying this definition right here and putting it here, and let's put it in math terms because it helps compute and proof. We say the limit exists and is equal to L, so the notation we discussed last video, limit of f of x is equal to L, so the limit as x approaches x naught of f of x is equal to L. That is what this means. If and only if, so we'll write a logical equivalence sign for all positive epsilon, so for all epsilon greater than 0, there exists some positive value for delta. There exists is the backwards E, remember? This upside down A is for all or for every, and the backwards epsilon is there exists. Very important to remember. We're going to be using that a lot in our proof. Such that, so we'll just write, normally we might write such that like this, or we'll just omit that and write a parentheses. If, remember, x belongs to the delta neighborhood, not excluding x naught, which is what we defined up here, and then this then, or this logically implies the following is true. The f of x is inside the epsilon neighborhood, or as we can see right here, as we defined up here what it means. So the limit as x approaches x naught of f of x equals L if and only if, or is a logically equivalent to, for any epsilon greater, for all epsilon greater than 0, there exists a delta greater than 0, such that, we omitted such that, but you can write that, 0 is less than the absolute value of x minus x naught is less than delta, or the absolute value is a distance function. So the distance between x and x naught is less than delta, which implies that the distance between f of x and L is less than epsilon, or the absolute value of f of x minus L is less than epsilon. And this is our complete definition of a limit. We have figured it out. Now, if they ask us, well, how do you really define a limit? Skeptics, no more. We have a definition now. No more skepticism about our idea. We have a straightforward test for a limit 100% definitively. But how can we actually use it? Because while it's great to have that, how can we actually prove stuff? So first, let's actually look at what the proofs, what we have to prove. So if we want to prove this is true, we actually have to prove that for any epsilon given, there exists a delta. There exists, well, one way to prove something exists is to actually find it. If I want to prove that there is a Burger King in the next mile radius, I don't know, circle, whatever, circle, there's a mile radius, then I can find that Burger King, and that proves its existence. Or for anything, if I find it, then that proves its existence. So in this case, what we're going to do is that we're going to find delta in terms of epsilon. So here's an example to actually exemplify how it would work. So the limit as x approaches 0 of f of x is equal to 0. In this case, our x naught, which is known as the accumulation point, is equal to 0, and f of x is equal to x, and the limit is equal to 0. So we can substitute that into our equation, or definition. I forgot how to speak English for a second. So for all epsilon greater than 0, there exists delta greater than 0, such that the following is true, where 0 is less than the absolute value of x minus 0 is less than delta, implies that the absolute value of x minus 0 is less than epsilon, and we're plugging in our 0 is our x naught, and our L is also 0, and our f of x is x. So notice these two are literally the same thing. This is why this proof is going to be the easiest one. Now, when we're proving this, one method that we're going to be doing throughout this course is that we are going to start at this part, the right, and we're going to end here. But since we're trying to imply this, we have to go in this direction. We can't go backwards. That would be fallacious. So what we're going to do is that we're going to start here, but we're going to begin implying backwards, right? So remember, green flag, maybe no racing, and this is a very poorly drawn checkered flag. We end here, we start here. Let me show you an example of what that would look like. So since we're writing our proof, we're going to write PF. So we're going to fix an epsilon greater than 0 such that, we're going to fix epsilon greater than 0, the absolute value of x minus 0 is less than epsilon. So remember, we start here. We're going to put this here, and we're going to just write it here. What does it mean to fix epsilon greater than 0? Well, remember, we said for any epsilon greater than 0. So we're just going to say, okay, let's say epsilon is actually greater than 0. So we're going to write this here, and now we're going to work backwards. We're going to have a backwards arrow. So right here, epsilon is greater than 0, so we can just do that 0 is less than epsilon, and we could just put something in the middle. That totally is fine. So 0 is less than the absolute value of x minus 0 is less than epsilon. Now, this proof is super trivial, as notice right here, we have our where we end, right? All we need to do is get to the end where we have this part. We want to reach this. This is our final goal. We want this right here, or x minus x naught, to be an absolute value, right? The 0 less than, pretty trivial, but this is where we want. And once we're here, we're just going to take whatever is on this side and choose delta to be that. This is what we're doing. We're defining delta to be epsilon, or we're choosing it to be that way. So choose delta equals epsilon, and we're done. We can just fill in our little box. For example number 2, we're going to prove that the limit as x approaches 3 of 2x plus 5 is equal to 11. Now, how do we prove it using epsilon delta? Well, the limit as x approaches 3 of 2x plus 5 is equal to 11 if and only if, for all epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus 3 is less than delta, implies that the absolute value of 2x plus 5 minus 11, so this is our, notice that this is our f of x, and that this is minus L. So we have f of x minus L is less than epsilon. Now we start here, so we're going to write PF for proof, where you can just write proof. Fix epsilon is greater than 0. Remember, that's the first step. And then we start here. This is our kind of anchor point. And since we're working backwards, it's technically our end, but we're going to write start. We're going to start here. Now we're going to draw a backwards arrow, which means that is implied by the fact that the absolute value of 2x minus 6 is less than epsilon. Positive 5 minus 11 is negative 6, which is implied by, we're going to factor out a 2, and we're going to use the multiplicative property to take it out. The absolute value of 2 times the absolute value of x minus 3 is less than epsilon. This step can be omitted. You don't have to do this step. You could just jump straight here. I'm just doing it for the sake of example. So we factor out the 2, and now remember, what do we want? Look, we have to keep our objective in our mind. We want to get here, the absolute value of x minus 3. Notice we have the absolute value of x minus 3 right here. All we have to do is isolate it. So we're going to divide by 2 on both sides. Divide by 2. So that is implied by the absolute value of x minus 3 is less than epsilon over 2. And we have isolated this. We're almost done. We just need to write that since epsilon over 2 is always positive, is epsilon, as we said, is positive. We fixed it to be that. That is implied by 0 is less than the absolute value of x minus 3 is less than epsilon over 2. And since we have this, we do our final step, equals the colon delta, or we define delta to be epsilon over 2. We choose delta to be epsilon over 2, and we found it. So it's like a formula. I plug it in. You give me epsilon equals 0.2. I can tell you right now that delta can be 0.1, and it works right here with proof. So we have shown how to prove basic linear functions limits. However, what if we get some harder functions like square root or polynomial functions? Here's an example. Prove the limit as x approaches 4 of the square root of x is equal to 2. So we'll rewrite that here. This is true if and only if. Remember, we have to memorize the definition. For all epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus 4 is less than delta. Remember, x naught is 4. Implies that the absolute value of fx minus L, the square root of x minus 2, is less than epsilon. Let us write. So we're going to write proof, and we're going to start. So fix epsilon greater than 0. Remember, always write this in any epsilon delta proof. Now we're going to prove that there is the existence of our delta. Remember, we start with the right, so we'll write down this here, that is implied by, if you remember from algebra 2 or pre-calculus, you might have learned what the conjugate of of um, of an expression is. In this case, we're going to multiply by the conjugate and then divide it so that they cancel out and become 1. But we're going to multiply by the conjugate here because you'll see why in a second. Because if we're just here, we can't factor anything out. It looks like we're stuck, so we're just going to multiply the conjugate. It's always a good idea. This is less than epsilon. That which is implied by the absolute value of, we're going to multiply out this. Remember, this is the difference of squares, which will get us the absolute value of x squared minus 2 squared, which is x minus 4 over, we're just going to rewrite this here, is less than epsilon, which is implied by, we're going to use the multiplicative property again to split these two absolute values less than epsilon. Here we have to make an observation. We have to observe the following. This is implied by, we have to observe that the absolute value of x plus 2 is actually greater than 1 for any real x. You give me any x and it's greater than 1. Why? Well, this just means that if and only if the absolute value of x is greater than minus 1. And we know this is true because the absolute value of any number is always greater than or equal to 0. So of course it's greater than negative 1. Now, let's take a look because we have to have an idea to get through this. Well, if x is some number less than, let's say, epsilon, it could be a k, it could be whatever, then that implies that x over 2 is less than epsilon. Do you agree? Because I have 2 is less than 3, and if I divide 2, then I get 1 is less than 3, so, which is also true. It's quite trivial. In fact, for any number greater than 1, k, if x is less than epsilon, then that implies that x over that k, for any k greater than 1, remember if it's 0.5, for example, what we said does not hold, because if we have 2 is less than 3, but then we divide 2 by 1/2, then we can remember 2 over 1 over 1/2. We go here, here, and we get 4, and 4 is not less than 3. Remember, we get here, 4 is not less than 3, so it has to be greater than 1. So this is true. This statement is true. So if we can prove that this denominator is indeed greater than 1, we can just completely delete it. And in this case, if you are a bit confused, I can explain it a bit more. This number is smaller than epsilon. We're working backwards, so how about we start here? So let's say this is true, x minus 4 is less than epsilon. Well, can't we also say that if we divide by a number greater than 1, in this case this is greater than 1, this is going to get even smaller, so it's going to be less than absolute value of x minus 4 over this greater than 1. We can divide it by any number because that's still going to hold true as we just showed here. So for that reason, since we're going backwards, we can just delete it, right? And ignore it. Since it's greater than 1, we can just focus on here. Remember what we're looking for. Our target is to get the absolute value of x minus 4, which we have here. So our final step is just to say 0 is less than that, x minus 4 less than epsilon, and we can simply define or choose our delta to be epsilon now, and we're done. Sometimes we must notice when certain parts can just be omitted, deleted, whatever, right? In this case, the absolute value of x plus 2 is greater than 1, so we just ignore it. Example number 2, we're gonna go to polynomials. So prove the limit as x approaches 0 of x to the power of 7 plus 3x to the 4 plus 3 is equal to 3. First, let's say we didn't even have this. If you saw last video, you would know how to compute it. We try plugging it in. Plus 3 times 0 to the 4 plus 3. This is 0, so plus 3, so we just get 3. So this seems to be right, but now we're going to actually prove it. we have to go over a few things, so just some concepts. Before we start, we must define what this minimum is. So let's say S is a set. The minimum of this set and the maximum of this set. So the minimum of set S, which is denoted as this, is simply the smallest element of S. An example of this might be we have the minimum of 2 and 3, then in this case this is equal to 2 because 2 is the smallest element of the set. And likewise, the maximum of set S is just the largest element of set S. So also, if we say X is less than the minimum of between actually any set, but for simplicity, we're just going to do A comma B, then we know that X is less than A, then X is less than A, and X is less than B. But why? Well, we can say without loss of generality, this is just something we write. We'll just say A is less than B, right? So we can say that the minimum between these two is equal to A. Otherwise, A is less than B, right? If A is less than B, then the minimum between this is going to be A. So if X is less than the minimum between these two values, then X is less than A. But since we know A is less than B, then X is less than A is less than B. Therefore, X is also less than B. So we just proved that if X is less than the minimum of two numbers, then X is less than both numbers. Another concept that we're gonna come back to, it's a little light bulb. Also, X plus Y is less than K is implied by X being less than K over 2 and Y being less than K over 2. Because if we add the two inequalities here, we'll just get X plus Y is less than K over 2 plus K over 2 is equal to K. So this is implied by that. Also, for notation purposes, this, like an arrow pointing up means and, an arrow pointing down is or. This is also known as a conjunction, junction, and this is known as a disjunction. Back to the limit, now that we have the pre-required knowledge. So, the limit as x approaches 0 of x to the 7 plus 3x to the 4th plus 3 is equal to 3 if and only if, for all epsilon greater than 0, there exists delta greater than 0, such that 0 less than the absolute value of x minus x naught, or x naught is 0, is less than delta, implies this, right, our f of x, we're just rewriting it, minus 3, and notice the 3's cancel out, so in the next step, we'll just completely ignore this, is less than epsilon. So proof, fix epsilon greater than 0. Always, first thing we have to write, don't forget it. You will lose points on your calc exam if you do forget this. So, we're going to remember, start with the right side. We're going to write that down. That is implied by the following, right? We're just going to cancel out the 3 and the minus 3, which is implied by, so notice that the absolute value of x plus 7, x to the 7 plus 3 to the x to the 4, is by triangle inequality. If you remember what is triangle inequality, the absolute value of a plus or minus b is less than the absolute value of a plus the absolute value of b. This can be proven for more than 2. In fact, it may be proven for 3 or 4, whatever. There are even some proofs that have Cauchy-Schwarz inequalities. It can get very complicated. It's very interesting, but we don't care about the proof right now. We only care that this is true. So by triangle inequality, the sum of these two inside the absolute value is less than or equal to. We'll split them off, and we'll say that this is less than epsilon. This is, are we just assuming this to be true? Well, we'll move on and show why this is true. But we showed that if this is true, then this is true. That's the important step. Remember, since we're working backwards, right now we just have to prove that this implies that. That is implied by, remember, from our light bulb idea up here, we can split this and this. So, since we're working backwards, the absolute value of x to the 7 is less than epsilon over 2, and this is less than epsilon over 2, which is implied by this to the 7. We're just going to take the 7 out of the absolute value. It's a valid property, less than epsilon over 2. And we're going to take out the 3 and take out the 4 is less than epsilon over 2, which is implied by this. The absolute value of x is less than the 7th root of the following, and the absolute value of x to the 4th is less than that. And we're going to keep going, but the absolute value of x is less than the 4th root of epsilon over 12. I'm just rewriting this here and putting this here. And remember, both of these have to be true, which is implied by 0 being less than the absolute value of x is less than the minimum between these two values. Remember, we established this right here, that if x is less than the minimum between a and b, then x is less than a and x is less than b. And since we're working backwards, let's just go over here. The absolute value of x is less than the minimum between these two. Therefore, the absolute value of x is less than a. The absolute value of x is less than b. So this is actually a valid step. Maybe sometimes it might get a bit confusing because we're working backwards, but as long as you go from here to here and prove it, then you'll be fine. Finally, we have our absolute value of x, which is exactly what we were looking for as we wrote right here. We can just write the absolute value of x since it's x minus 0. And in this case, we'll just say that we'll choose delta to be the minimum between these two values. In general, if we have the limit as x approaches x naught of a polynomial function where p of x is the polynomial function, we must use the triangle inequality and end with some minimum function. That's just like a structure we'll learn. So here's our final practice. You can pause the video if you want right here. 1 through 3. Okay, so let's work with number 1. So notice that when we have the following limit, so we'll just rewrite. So we have to evaluate and prove. So we'll rewrite this here, and we'll evaluate, which is the first step. X approaches 4, so 3 times 4 minus 2, which is 12 minus 2, which is 10. If and only if, and we'll write the definition for all epsilon greater than 0, there exists a delta greater than 0, such that 0 being between the absolute value of x minus 4, remember x naught is 4, less than delta, implies that the absolute value of 3x minus 2 minus 10 is less than epsilon, so f of x minus L. This is 3x minus 12. We'll get into that in just a second here. So here's our proof. If you did this, you will get points, full points. I'll say if a certain step can be omitted or not. So fix epsilon greater than 0. The absolute value of 3x minus 2 minus 10 is less than epsilon. Remember, we start here, we end here. This is implied by, remember, we just do minus 12, less than epsilon, which is implied by, we factor out the 3, less than epsilon, which is implied by, we divide 3 from both sides. And remember, what are we looking for? The absolute value of x minus 4. We found it here, so our next step is just to write 0 is less than that. And that's less than epsilon over 3. So we'll just finally, now that we have that, write equals colon delta, or we choose delta to be epsilon over 3. We're done with our proof. Number 2. This limit, as x approaches 2, is, well, the absolute value of 2 times 2 plus 4, which this is 2 plus 4, 6. We evaluated 6. That's the easy part. Now we have to prove it. For all epsilon greater than 0, there exists delta greater than 0, such that 0 less than the absolute value of x minus 2 is less than delta, implies that the absolute value of the square root of 2x plus 4 minus 6 is less than epsilon. I won't talk too much through this because I'll just show you through the math. Fix epsilon greater than 0, f of x minus the absolute value of this minus epsilon is implied by, we'll just do 4 minus 6 minus 2, which is implied by, we're going to take we're going to multiply by the complex conjugate. We're going to, this is a difference of squares, so this is implied by 2x minus 4. Remember, up here, we have just square root of 2x squared minus 2 squared, which is 2x minus 4, as you wrote right here, and over this is less than epsilon. And I omitted the step where we put here, 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 here. You should write that on your exam. I don't know if it's optional or not. It might be. So notice how this is always greater than 1. Whenever we're doing this with a square root function, this can always be greater than 1. It's kind of a rule of thumb, maybe. I'll show you why this is true so you understand it. But you just write this is greater than 1. You might have no idea what it means, but you can always write this in a square root function. And then we just delete this, and why is this true? Well, this implies, since we're reading it backwards, that this is a lower number than this, so obviously this implies that. We factor out a 2, so this is implied by that, and this is implied by that, by dividing by 2, and this is implied by, remember, what is our target? Well, our target, we've reached it. So 0 is less than our target, the absolute value of x minus 2, is less than epsilon over 2, and once we reach this state, we can just choose delta. That way, we reach, actually, the following step is less than delta, which since we're reading it backwards, is saying that this implies all the way up here that this implies that. Our final limit is a polynomial function. The limit as x approaches 0 of the following function is equal to 0, because notice as we plug in 0 to all of them, we get 0 plus 0 plus 0, which is just 0. If and only if for all epsilon greater than 0, there is a delta greater than 0, such that if 0 is less than the absolute value of x minus 0 is less than delta, implies that then the absolute value of 11x to the 5th, so our f of x, and notice I could have wrote minus 0 because our limit is 0, but I'm not going to do that. But you should write that if you want to. It's an epsilon. So fix epsilon greater than 0. We're going to write this down here to be our f of x, which is less than epsilon. Remember, that's our starting point, and we're going to work backwards. This is implied by the following. We're just going to rewrite it. And notice we have, by triangle inequality, this is less than or equal to. We're splitting the terms. Here, I should write, this is just the absolute value of 11. Okay, this is a bit confusing. This is the absolute value of 11x to the 5th. This is the absolute value of 3/2 x to the 3rd. And this is the absolute value of 2/3 x. We're just applying absolute value rules. This is all less than epsilon. This is implied by, notice how many terms do we have? 1, 2, and 3. So what number we're going to divide by? Remember our big idea? We're going to divide by 3. That way when we add them up, we get 3 times epsilon over 3, which cancels out. Sorry, 3 times epsilon over 3, which will cancel out, which is epsilon. So right here, we're going to get the following is true. Remember, we're just taking here, we're putting it here, here, we're putting it here, and here, we're taking it from here. They're all less than epsilon over 3, and, which is implied by, we're going to do some algebra. Notice we divide by 11, take the 5th root. And we multiply by the reciprocal 2 over 3, and take the cubed root. And finally, well, the easiest case, we just multiply by 3, divide by 2, so the 3's cancel out, and we just have, I apologize for the mistake here. This should actually be epsilon over 2, which is implied by, remember, we reached the absolute value of x here, so we're going to write 0 is less than the absolute value of x is less than the minimum between all this. Remember, this is epsilon over 2. I apologize again. It's the minimum between these three values. Whichever one's the smallest, this is going to be picked. And since we've already reached our target, the absolute value of x is less than delta, we can just write that this is our delta, and we're done. So that's the end of our proof. Hopefully this helped you learn through what an epsilon delta proof is and how to actually write one. And this was a bit long, but I wanted to make sure that all the steps were completely clear and comprehensible, and that it was all also intuitive and rigorous. Thanks for watching.